All right, good. Hello, class. I'm gonna say good morning. So in this video, we are going to continue our discussion about planes and surfaces. So we really have talked enough about planes, I think. What I want to do is really take a closer look at surfaces and using traces to kind of help us visualize what our surfaces look like. Okay, so that's really what we're going to be focusing on here. Okay, and our traces are the xy trace when z is equal to 0, the xz trace when y is equal to 0, and the yz trace when x is equal to 0. So what we're doing here is we're basically isolating it to the main perpendicular planes that correspond with each of the axes and getting it's called a trace for a reason. We're basically getting a trace, or I like to call it the skeleton of the surface. Okay, so we looked at this briefly last time when we were looking at planes, and I think the best way to actually talk about this is to just do an example. So let's look at an example, take a look at the traces, and then see how they fit together. Okay, so the first example we're going to look at is x squared over 9 plus y squared over 16 plus z squared over 25 is equal to 1. This is basically this version of a surface. The f of xyz is equal to 0, because what you would do is you'd move the 1 over and get it in this form. Okay, so this is not a z equals a function of x and y because it's a z squared type thing. Okay, now, all right, so if we remember back to our Cartesian formulas, if we had an x squared plus a y squared, let's say over just 9 over 16 is equal to 1, this is actually an ellipse. Okay, now when we add the z to it, you could probably guess that what this does is either creates a spherical kind of thing, and what this actually ends up being called is an ellipsoid. And for whatever reason, that is the ellipsoid, the oid part is what they tend to use for moving into 3 dimensions. So like paraboloid, ellipsoid, hyperboloid, etc. Okay, makes it sound kind of sci-fi-ish or B-movie-ish, but those are the terms. So what I've actually drawn here is the xy trace, right? The xy trace when z is equal to 0 is this. It's an ellipse. So we have x squared over 9 plus y squared over 16 equals 1. And what this looks like, okay, how ellipsoids work is if it's x squared over 9, that means x has a radius, so to speak, of -3 to 3. Okay, in the y squared over 16, we have a quote-unquote radius, let me try to match these a little better, of 4. Really, it's called the major and minor axes, but I think of it as the x radius and the y radius. Okay, so we get this sort of shape here. Okay, so this is what's happening on the xy plane. Okay, is this ellipse. All right, now let's look at the next trace, the xz. Now, this order is not, mandatory or anything. It's just the order I like to go in. Okay, so the xz trace, that's where y is equal to 0. So we'd get x squared over 9 plus z squared over 25 equals 1, and this is another ellipse. Right, and I always draw my traces with z as the vertical axis, unless it's the xy plane, then of course y is the vertical axis. But just like before, x has a quote-unquote radius of 3, and z, since it's over 20, z squared over 25, has a vertical radius of 5. Okay, so it looks like this, if I can draw it. All right. So there is the XZ trace, and I sometimes do this. I'm putting a pink line here because we're looking at this straight on the side, and so really there is that XY trace here. Okay, it's just we're looking right on it, and then here, this is the so X and Z is coming out this way, right? So really, looking at this from above, we would see the purple line of this. Okay, where really it's sort of coming out this way. All right, now let's look at the third trace, which will be the YZ trace. Okay, so this is where x is equal to 0, so we'll get y squared over 16 plus z squared over 25 equals 1, and this is, what do you know, another ellipse. Okay, so if we were to graph, all right, we'll go 4 in the y direction and 5 in the z direction. Okay, and that will be our ellipse, which of course I can't draw super well. Okay, so that means over here the YZ is going to look something like this, but it's actually coming out into the z direction. So you can kind of start to see, YZ. Here is the XY trace. This would be the YZ trace. Whoops. All right, when you're looking at it head on. And then this one, when we're looking at it, X is coming out this way. So the XY trace would be here in purple, or sorry, pink. Right, so it would be coming out sort of this way, whereas in purple would be the XZ trace, which looking at it head on would just look like a line in this direction. So when we put all these together, what we're going to have is basically like a football shape, right? It's going to be what's called an ellipsoid, or an ellipse that has been extended into 3 dimensions. All right, now if we put these things together on the XYZ space, in 3 space, here's our first trace along the XY plane. So here we are at 3 in the X and 4 in the Y. Here is the XZ trace. Okay. Right, so as I said, when you look at it straight on, that's sort of what you get. And then here is the YZ trace. And when we take all 3 of them together, we get basically the skeleton of this surface. Okay, so if I get rid of the axes here, we can see a pretty good representation, okay, of the ellipsoid. All right, let me bring the axes back because it's not rotating right in the center. Now, if I actually put in the surface itself, here's the surface itself, and you see what the traces are doing. They are basically like I said, showing the skeleton of the graph. Okay, so that's what traces do for us. They give us a nice way to help us represent the surface itself without maybe needing software, because a lot of times actually putting this into software isn't actually possible, but we still might want to know what it looks like. All right, so for our next example, let's look at the function z equals 1 minus x squared over 16 minus y squared over 4. This is more the z equals f of x, y, right? And let's just start looking at the traces. We'll go in the same order. So we'll check out the xy trace in pink. We'll check out the xz trace in purple. And the yz trace in orange. Okay, so for the xz or the xy trace, excuse me, that's where z is equal to 0. So I'll plug that in and get 0 is equal to 1 minus x squared over 16 minus y squared over 4. Okay, what I'm going to do is move these negative guys over to the other side to get x squared over 16 plus y squared over 4 is equal to 1. And here we have another ellipse. Okay, and I will graph that kind of quickly. Right, we'll have 4 in the x direction and 2 in the y direction. Right, so here's our ellipse in the xy plane. Right, now next we'll look at the xz trace. So the xz trace, this is where y is equal to 0. Okay, now when y is equal to 0, we get this right here. This is our z is equal to 1 minus x squared over 16. Now this is actually a parabola. Okay, it's a parabola with, in this case, z-intercept equal to 1. And x-intercepts, well, the x-intercept should be negative 4 and positive 4, because if we put it in plus or minus 4 here, we'll get 0. So we should have x-intercepts negative 4 and 4, and z-intercept 1. So it should be a fairly shallow parabola, which makes sense because we're putting a 1 over 16 in front of our x squared. Okay, then next up, and last but not least, this will be our yz trace. The yz trace is when x is equal to 0. And we're going to get z is equal to 1 minus y squared over 4. And again, that's another parabola. Okay, so when we go to graph this, and again, I'm just doing quick sketches here. It doesn't have to be exact. I'm just trying to get an idea of what it looks like. Okay, so what's going on here is, once again, the z-intercept should be 1, and the y-intercepts should be negative 2 and 2. Okay, so a little less shallow of a parabola than we got here. Now, what's actually happening, I'll look at the xz trace here and fill in the other pieces. the xy plane, well, y is coming out this way. Okay, so it looks like we have an ellipse here, and then a parabola, since this is the y, parabola coming out this way. So it looks like we've created a bit of a bowl shape. And here, if I do it in this direction, so here it's the x coming out this way. So the xy trace should look something like this, and the xz trace should come out this way. All right, so it looks like we've created basically a downward facing bowl. Okay, notice I didn't really do much on this side, mainly just because it would be kind of hard to tell what's going on. It's easier to see what's going on if you use either the XZ or YZ trace to kind of get an idea of what the 3D effect is happening. But let's put these on an actual 3D graph and see if it lines up with what we just put together here. Okay, so here's our 3 space, and there's our first trace on the XY plane. There's the ellipse. There's the XZ trace, which is the parabola. Okay, and then the YZ trace, which is the other parabola. So when we put them all together, we can see we've created a sort of bowl shape. Okay, let's get rid of the plane for a second here. So we can see how these sort of fit together now. And if I actually put in the surface itself, we can see that it's giving us a bit of a nice skeleton of how the surface is behaving. Okay, now this is called a paraboloid. And it's basically when you take, you can think of these as solids of revolution from Calculus 2. So in Calculus 2, when you would take a parabola and spin it around the x or the y-axis, you would get this like bowl shape. That's essentially what we're doing here, except we're allowing that parabola to change, because as we can see, this parabola is steeper than this parabola, right? So that's the power of creating surfaces this way, is that we can have it not just be a nice, perfect solid of revolution. It can act more like a boat. This almost looks like the bottom of a boat. All right, so let's look at one more example. And what I hope this example shows is that traces can't be our only tool, right? Traces have quite a few limitations. Right, they're very good at detailing what a graph is doing, in a sense, if it likes to congregate around the origin, but if it has any sort of weird behavior, sometimes it can be difficult to really wrap our head around what shape it's portraying just from the traces. All right, so they can't be our only tool, despite the fact for a lot of cases they are a really strong tool. And so in the next section, that's what we'll be talking about, is the second tool. So these two tools together are what will, make us be able to better visualize these things. Okay, so it can't just be traces alone. But anyway, let's take a look at the traces for this particular function here. So the xy trace, of course, that's when z is equal to 0, gives us this. 0 is equal to 1 minus x squared over 25 plus y squared. Okay, I'm going to jump to the formulas first, then start looking at the graphs. So then the xz trace, that's when y is equal to 0. That's going to give us z is equal to 1 minus x squared over 25. And then the yz trace will be z is equal to 1 plus y squared. All right. So I'm going to go backwards through these. Okay. Our first one, whoops, let's try that again. Our first one is a parabola, right? This is a parabola again on the YZ plane. And in this case, notice all I've really done from the pattern last time, I changed some of the numbers, but I changed this to a plus. Instead of minus minus, it's minus plus. Now this is a parabola that opens upwards. Okay. Our next trace is another parabola, but this time it's opening downward since it's a minus. So if I look at this xz trace, right, it has the same y-intercept, which is 1, and the x-intercept should be, or intercept should be negative 5 and 5. All right, not drawing these super well, but again, I'm just trying to get a basic idea of what's going on. And then here, and this is where things get a little weird, okay? Because this trace, if I move these over now, I'm going to get x squared over 25 minus y squared is equal to 1. This is no longer an ellipse. This would only be an ellipse if I had a plus, but since that's a minus there, this is a hyperbola. Okay, and how you graph a hyperbola, I think a lot of people probably don't really remember this because it's not something that shows up a whole lot. But we'll see it quite a bit in this class. Okay, what we do is we keep the same idea before. The x moves out negative 5 to 5. Okay, and the y here, negative 1 to 1. But instead of making like an ellipse, what we do is we draw a little box. Okay, and then from corner to corner of those boxes, we draw a line going through the origin. So something like this. Okay, so now a hyperbola either is two parabola-looking things opening upwards or opening sideways. Now, if you forget which is which, like how do you know whether it opens sideways or not, it has pretty much everything to do with which one of these is positive. Because if I put in 0 for x, that would be us being on the y-axis. But if I put 0 in for x, say that disappeared, you'd have negative y squared is equal to positive 1. That's impossible, right? So x can't be 0 in this particular case, right? So we can't live on the xy plane, or sorry, on the y-axis, okay? Instead, if y was 0, so if we lived just on the x-axis, we'd get x squared over 25 is equal to 1. So x squared is equal to 25, so x is negative or positive 5. Okay, so a hyperbola opens in the direction of the positive piece. Okay, so, and then it does this. It basically makes a parabola-looking thing that sort of tries to hug these lines we just made. Okay. And it should be symmetrical, but of course I'm not drawing these super well. But there we go. this is what's happening on the XY trace. Now, this is actually kind of hard to visualize what's going on, because if I tried to put these guys together, well, on the YZ trace, it's opening upwards, so it would look something like this. And on the XY plane, we get like hyperbolas, right? So let's actually graph this on a 3D plane or a 3D box and see what we get. All right, so if we look at this on a graph here, let me get this. There we go. Positive X, positive Y, positive Z. Here is that hyperbola on the XY plane. Okay. Here is, so that's the XY trace. Here's the XZ trace, which is that downward facing parabola. And then here is the YZ trace. Now, just based on these traces, it's actually kind of difficult to tell what in the world this thing looks like. In fact, I'm going to show off my nerd a little bit here, but this almost looks like that one Pokemon that's all the magnets facing in weird different directions. I guess I'm losing some nerd cred because I don't really remember its name. But like the other ones, I could actually visualize how the surface fit around this. Here, I'm having trouble doing that. So let's take a look at the surface itself and see what we get. All right, I actually just realized that even though it looks pretty much the same, I had the graph sort of shifted wrongly. Anyway, if we put in the surface here, we get this weird looking thing. All right, and let me, okay. I was trying to get it more bounded. It's kind of hard to do, but yeah, it looks kind of like a really odd surface. It almost looks like a Pringle, except it goes off infinitely in either direction, right? So my point with this example is that traces aren't always enough to help us visualize what's going on, okay? We need more tools, and so that's what the next lecture is going to be about. We are going to take a look at the next tool, which is contour or level plots. And these two things together are a really good way to help us visualize all of our surfaces that we'll be looking at. All right, and that will be good enough for this part 2. And the next one we'll come back and talk about those contour plots, and then we'll start talking about how calculus works with all this.